Cool. All right. Hello, everyone. Today, I'll be walking through this paper called Were RNNs All We Needed by Borealis AI and University of Montreal, and notably Joshua Bengio is one of the co-authors of the paper, which is cool. And the title of the paper, as you notice, is a bit tongue-in-cheek. It's referring to Attention is All You Need paper, and subsequently all the other X is all you need papers. And I think that the point it's trying to make is that that they're revisiting old architectures or older architectures, in this case, recurrent neural networks, and looking at how they can be adapted to meet the kind of modern requirements and ideas of and scale and speed of training and inference of newer architectures like transformer models. And they innovate on the recurrent neural network architecture to increase the training speed and make them more viable for some of the tasks that transformers and other state space models have shown to be quite good at. So it's actually relatively short paper. So we'll definitely get through it in the time we have today. But really the problem that they're approaching is that obviously transformers have seen a lot of success, and they've seen a lot of success because they're quite parallelizable during training, which means it's feasible to train really large transformer architectures. And however, they have a limitation, right, which is that transformers are scale quadratically for in terms of sequence length. So they obviously have this limitation that we can't just keep scaling the sequence length infinitely, because we pay the cost of scaling them. However, other recurrent architectures don't suffer from this problem. So we've seen architectures like state space models, Mamba, which is an evolution of those, and those that have shown quite good performance across a variety of tasks. And so this paper basically revisits recurrent neural networks, specifically LSTMs and GRUs, gated recurrent units, and explores how can we get past this limitation of backpropagation through time, which makes them quite slow to train. So we'll go through this, but they introduced two sort of modified versions of LSTMs and GRUs that are smaller in terms of number of parameters, but more importantly, they are parallelizable during training, which leads to much, much faster training, which means we can scale them up, and then they match some of the performance across a variety of tasks that transformers and some of these state space models achieve. So as I go through this, feel free to jump in with questions. I'll try to keep an eye on chat as much as possible. And apologies if I sound a bit stuffy today. I'm working through a cold as well. Cool. So as I mentioned, transformers have obviously been quite successful, as we all know, but they have this limitation, which is this quadratic complexity in terms of the sequence length. So we really can't keep scaling the sequence length without paying a cost. So understandably, there's been a lot of different research into how can we get past this limitation, or what are other potential architectures that we can explore for problems which require very long sequence length. And this has led to a couple of different avenues. So one is the exploration of recurrent sequence models. So the Mamba paper, which has gained quite a lot of attention, which is a state space model. And it builds off previous state space models that have been developed. I won't go into, or maybe later we can go into the detail of those if people aren't aware of those architectures. But they are recurrent in nature, and they're actually quite similar. And they talk about this at the end of the paper. They're actually quite similar to you can pose them as recurrent neural networks as well. Then another sort of family of or another avenue of research has been how you looking at the attention module. So I guess attention is what makes things scale quadratically with transformers. So what are like modifications that you can apply to attention to try to improve the efficiency of training and also efficiency of inference and scale the sequence length. So they look at RNN, which is a fairly new one, I think. I must admit I haven't looked into it in much depth, but if anyone has, I'd love to hear thoughts at some point. So yeah, they say, well, why don't we revisit recurrent neural networks and see what we can do to try to improve their scalability to like long sequence lengths and their training performance. So what they look at is they look at actually, I won't go into this now, but the sort of like TLDR of things, I guess, of the change they make is that what makes LSTMs and GRUs slow to train is this backpropagation through time. And the reason you need to do backpropagation through time is because each the parameters always depend on the input xt and the previous output ht minus 1. And because of that, you have to backpropagate through all of the time steps to be able to get like the gradient to update the parameters. Now, like the reason transformers and other models are, or transformers specifically, are more efficient to train is because there's not this limitation that you have to backpropagate through time. In fact, like transformers, if you think about it, they don't have this concept of like a sequence. In fact, you have the positional embeddings and the input embeddings, which are concatenated, and then you apply the attention. You attend over all of the sequence. But what that means is you can do the backpropagation more efficiently, and it uses this algorithm called the parallel scan algorithm, which we'll talk a little bit about later. But effectively, that means that you can train in parallel, so therefore much more efficiently than if you have to do this backpropagation through time, as you have to do for the traditional LSTMs and GRUs. So a little bit of recap. This was quite fun because I haven't looked at LSTMs and GRUs for, gosh, like quite a few years. So they go through the formulas here, but I always preferred actually looking at the, oh, does this not show? Looking at the actual like image of these. So this is an LSTM cell, and you've got quite a few things going on here, but hopefully I'll walk through. Can you see this? Yeah. Okay, I assume that's a yes. So the what you've got going on here is so for the LSTM guys, there's three sort of inputs. There's obviously your input xt. So if you have a sequence, this is the token at time step t. There's the output of the previous time step, ht minus 1. And then there's the memory, also otherwise referred to as like the cell state at that time. And then there's a bunch of different like gates here. And each gate here serves a different purpose. So the forget gate basically looks at how much of the previous cell state do we want to keep. You can think of it like that. So it looks at the input, the hidden state, the previous hidden state, and the memory, and says, okay, how much of this previous cell state do we want to keep? Conversely, the input gate does the same thing, but it looks at this new candidate cell state or candidate memory, and says, okay, how much of this new candidate cell state do we want to include in this final output? And this, so the combination of this, all of this here, creates the new cell state CT. And then you take this CT and you say, okay, what do we want to output as the new HT or the new hidden state? So then this output gate sort of determines how much, or like how to scale, I guess, this memory to get an output. So lots of different things going on, but I think the important thing to note here is obviously there's all of these are linear layers, and so they all have parameters, and all of these parameters depend on both the input and the previous hidden state. So this is why we have to backpropagate through time, because the parameters all depend on the previous hidden state. So you need to go through all of the hidden states of the sequence to be able to get the gradients for these parameters. So that's LSTMs. Then there's gated recurrent units. So gated recurrent units were proposed as a slightly... Yeah? Sorry, was there a question? No. Okay, cool. So they were a simplification of LSTMs. So they have one fewer, actually two fewer gates. Basically, instead of having the forget and input gate, which regulate how much of the cell state previous cell state you forget and how much of the current cell state you want to include, they have this update gate. And I'll show you the formula after because I think it's more clear, but this update gate controls how much of the previous hidden states and how much of the new candidate hidden state you want to include as the output. And then they have this reset gate, and this reset gate also controls basically how much of the previous hidden state you want to include in this new candidate hidden state. So it's a slightly simplified version. As you notice, they actually remove this concept of a memory and the hidden states as two separate things. So now they just have the hidden states, and those get passed between cells. So if we go back to the paper, that's effectively what's discussed here. So these are the formulas that capture all of the different gates. So in this case, this is the forget gate, the input gate. This is the candidate cell. And then here, when you create the new cell state, it's basically you take the previous cell state and say, how much do we want to include from that? And then the candidate cell state and say, okay, how much do we want to include from that? That creates your new cell state, and your output is a transformation of that cell state. It's actually quite a neat overview of LSTMs and GRUs, like quite a simple, condensed version. And then here's a similar thing, but for gated recurrent units. So you have, as I mentioned, the update gate and the reset gate. So the reset gate is what determines what this sort of new candidate hidden state is. And then the final hidden state is you take the update gate and you do ZT element-wise multiplication with HT and then 1 minus ZT. So the idea being here that these add up to 1, which actually controls, as far as I understand, basically controls for time dependence, in the sense that when you go through many time steps, it normalizes it, so it doesn't keep the hidden states don't keep scaling based throughout time. And so I think this introduces some sort of stability in the training as well. So this paper basically hinges on the idea that we want to be able to apply parallel scan to traditional recurrent neural networks, but this is not possible because of the hidden state. So before we go into that, so parallel scan is an algorithm that's used to compute. Let's say you have this function So Vt equals At times Vt minus 1 plus Bt. And you imagine you already have all the A1 to ANs and B0 to BNs. What this parallel scan allows you to do is it allows you to compute the sum from like UI plus, so imagine it allows you to compute U0, U0 plus U1, U0 plus U1 plus U2, et cetera, for all values like 1 to n in parallel. So rather than needing to do it sequentially, like through time, it's an algorithm that allows you to compute that in parallel. And obviously you can see how this applies with like sequences, in that rather than needing to sequentially compute each value in the sequence, you can basically just compute all of them at once in parallel more efficiently. I don't know the ins and outs of this algorithm. I haven't looked into it, but effectively that's what I've gathered from it. And if anyone has more in-depth knowledge, please feel free to jump in. But what they note is that if you look at this formulation, it actually looks quite similar to what we have in the update functions within the recurrent neural network. So actually, if you look at this formulation here, you can see that the H's are equivalent to the V's, and then 1 minus ZT would be the A's, and then this value here would be the B's. So we're close. We're close to being able to use the parallel scan algorithm, but we're not quite. And the problem is, as we saw up here, that both ZT and H tilde T are dependent on knowing the previous value. Now, if you remember what I said here, in order to use the parallel scan algorithm, we need to have all of the A's and all of the B's available ahead of time, so to be able to use the parallel scan algorithm. And in this case, we can't because we first need to compute what the HT minus 1 is to be able to have the A's and the B's. So what do? Well, here it explains what I just said, but I guess rather simplistically, all they do is just get rid of it, just get rid of this dependency. When I saw this, I was kind of a bit underwhelmed. Just like, oh, is that it? You just kind of remove it. But yeah, so they remove the HT minus 1 as an input to the update gate. They remove HT minus 1 from the reset gate, and then they remove the HT minus 1 to compute the candidate hidden state. And then they notice that actually the reset gate, its job is to control how much of the previous hidden state to include. So actually, we don't even need the reset gate anymore. So we can actually just have this really simple formulation, which is just like our candidate hidden state is just a simple linear layer on the input, and then our update gate is also a simple linear layer based on the input, and then they're combined to compute the new output hidden state. So now you can see that based on this, since we know the weights of these layers and we know what the inputs, all the x's are, we can now use the parallel scan on this formula. They also note here that the candidate hidden state uses a tan-h function, and this is to help stabilize the training. And the reason they apply that is because the tan-h, this h tilde t previously contained ht minus 1. So as you're like back propagating through it all, or doing a forward pass, if you don't normalize, then the gradients might vanish from like going from, because it's a large computation graph, and so training is a little bit fiddly. But since we remove the hidden states now, that ceases to be a problem in this case. So we can even remove this activation function and just leave it as a linear layer. I wonder what would have happened if they left it. They don't really go into it that much. They just sort of, I feel like they're in the mood to remove. I guess they maybe want to give it more, make it more expressive, I suppose. Like if you remove the tan H, it's maybe more expressive than, you know, squashing it to this -1 curve. So maybe that helps to build more complex functions, and we don't suffer from the vanishing gradient problem. So this is just a summary of what they do for the gated recurrent unit case. It actually has the additional benefit of reducing the number of parameters by a fair bit. So previously, the number of parameters was on the order of the dimension of the hidden states and the dimension of the input and hidden states. So it reduces it by a fair bit. And this improvement is noted even more when you consider here that in recurrent neural networks, what they say is that state expansion is usually performed. So the dimension of the hidden states is usually a factor greater than 1 of the dimension of the inputs. And the purpose of this is to basically learn features from the inputs, so be able to be more expressive, I guess. But because of that, when you actually scale the dimension of the hidden states, the number of parameters also, like as a percentage of what would be in the typical case, also reduces. So in the case that you use 4 times the dimensions of the input as the hidden dimensions, then it only uses 13% of the total amount of parameters. So like actually has the effect of like making the model fairly small. And much the same as gated recurrent units, they do the same for LSTMs. I'm happy to go over this. If you're interested, I'd suggest you just like read through it in terms of the differences, but it's actually super similar in the sense that all they do is they drop the dependency on the previous hidden state, and they apply some more simplifications here as well in terms of the tan H functions used for like stability of the gradients. They have to do one extra step with LSTMs to make sure that the output are like time independent, and so they apply some normalization basically. And this is what I mentioned before, where what could happen is like that the size of the hidden states or the scale like scales with time. So we want to make sure that the hidden states are time independent, so they basically stay like relatively stable. And so this is effectively turning this into a kind of normalization. And so then you end up with this kind of simplified LSTM where we remove some of the gates and some of the hidden dependencies. And the results are pretty like astonishing in terms of like speed, because now we can obviously apply the parallel scan algorithm. And so they have a few graphs here. So on the left, you see the runtime in seconds for an input of like varying sequence length. So we can see that for traditional LSTMs and GRUs, it scales linearly with sequence length. So we pay a price for like the increase in the sequence length, whereas for these, because of the parallel scan algorithm, it stays fairly constant. And so as a result, then the speed up is pretty dramatic as you get to long sequence lengths. So once you get to the 4,000 sequence length mark, we're looking at like anywhere from 1,200 to 1,600 times speed up in terms of runtime, which they give an example. I don't know if I highlighted at the top somewhere else, but basically it has the effect that if we were to train, where in a setting where min GRU would take a day to train for a fixed number of epochs, the counterpart GRU could take over 3 years. So the speed up when put as such is actually like quite dramatic, which means that we're now able to train these RNNs with much, much longer sequence lengths than we were able to in the past. So they kind of go over it here, but this is basically what they mention here. The last thing they mention is that obviously we get a much bigger speed up in training, but it comes at a slight cost of like a higher memory footprint when training these models. And the reason is because of the parallel scan algorithm, the computation graph is larger, and so it does require a little bit more memory. Well, in this case, almost twice as much memory as needed for LSTMs and GRUs. They mentioned that this is not that important in terms of the bottleneck for RNNs. Yeah, Damien?
I'm just curious, have they compared it to like the memory utilization of transformers?
No, and well, I guess no, they don't, because they actually only seem to compare to Mamba and other state space models, not as much transformers, which is kind of like something I feel like this paper is like unfinished as well, which is kind of something I was going to touch on at the end. It just sort of feels like the comparisons or the kind of experimentation and studies and results they could have done just don't feel like complete for me.
Yeah, that makes sense.
Yeah. But no, they don't compare to transformers. In this case, I think they do when you get down to some of the tasks that they explore. So so they kind of look at, they look at the runtime and the memory, and then they also investigate a little bit like the effect. Obviously we've removed an entire fundamental point of these LSTMs and GRUs, which is the fact that it can build complex functions because of the hidden state gets fed back every time, right? And so it can look at the previous hidden state, look at the new input, and apply some functions depending on those. But we've removed the previous hidden state. So what effect does that have? Well, it's quite interesting. So effectively, if you think of the LSTM, and imagine it's a one-layer recurrent neural network, right? Each gate or each cell will have like the new input xt, and the gates will have no access to the previous state, so they have no idea what came before because we've removed ht minus 1. So effectively, you can think of a single layer as being time independent, because the parameters can only learn from the input, not what came before it. So as a result, what happens is when you have one layer, you have a pretty trash model, because it's not content aware. It's not aware of like what came before it and then how to what functions to build based on the previous context and the current input. It can only look at the current input. In this case, they're looking, just FYI, at this task, which is called selective copying. As I understand it, it's basically you have a sequence of 4,096 tokens, and the task is that you have to copy 16 of those tokens, which are like data tokens, and return them in order as the output. So effectively, you have to like be able to memorize as you read through the sequence, what are the 16 tokens that you have to memorize, and then output them at the end. So naturally, if you consider that like a 1-layer LSTM or min LSTM in this case will not have access to the previous context, it's pretty bad at this task. However, as soon as you add a second layer, what happens is the outputs of the first layer now suddenly are time dependent. Because if you remember, the outputs of the first layer do consider the input and the previous hidden states, and those are used as the inputs to the second layer. So instead of having the time dependence within the layer itself, the fact that we're stacking layers allows us to build, allows us to create a picture over like the whole sequence. So, and you can see this, like as soon as the second layer is applied, the results that like the accuracy skyrockets because finally it has access to context, and it can reason over what came before and the current input. I thought this was quite like a good explanation of like how removing it doesn't. So you sort of have it's different ways of applying this like content awareness or like context awareness, and in fact, it's kind of parallel to what happened with the Mamba paper. So the Mamba paper builds on the S4 model. And the S4 model had a similar problem where the parameters are not like input dependent. And so they couldn't reason over like new inputs based on the context. Whereas the new Mamba model, I think that was one of the changes that they made, is sort of that they made the parameters input dependent. So depending on the token that they see, it can apply a slightly different function or transformation. So yeah, they look at a couple of different tasks to evaluate these models. The first one is, as I've mentioned, the selective copying, which is basically what I mentioned. So you have a sequence and you have to copy tokens out and output them. And as we saw here, it does really well with that. The second data set they look at is a reinforcement learning problem. I had to look this up because I wasn't familiar with, I'm not very familiar with reinforcement learning problems, but effectively these are like different environments where you have to get different shapes, so a cheetah, a hopper, a walker to like to walk effectively, and they're trained on. They look at how well they train on 3 different data sets of different quality. They mention in the appendix how these are created, and again, it performs like competitively with some of the later models. In this case, they do compare a transformer model, a decision transformer, RN, which is the softmax recurrent neural network, and then Mamba, and it's pretty comparable to those. And then last but not least, they also look at language modeling, where I thought it was quite fun that they used the Nano GPT library that Andrew Karpathy created. And they look at the character level GPT model for Shakespeare. If you're interested, Andrew Karpathy has a really good YouTube series where he talks through like this task, and he starts by building like really basic bigram models and builds it up to building like a transformer on this task. Really good YouTube series. But yeah, so they compare on this, and they find that it's comparable to like the losses are comparable to transformer models, but interestingly, they train significantly faster. So in this case, the Mamba model reached the lowest test loss at around 400 steps, the min-GRU and min-LSTM around 600 steps, but it took the transformer model around 2,000 steps to reach the same loss. Now, the question I asked myself when I saw this, and I want to ask it to the group, is like, doesn't this depend as well on like what hyperparameters you use? Like, I guess I was just a little bit like skeptical when I saw this. Or like, how do you ensure that this isn't just dependent on what hyperparameters you use?
I guess they could have done some sort of ablation and like tried different hyperparameters and average out of how these models do. But one thing it seems to me here is that, isn't it true that like the transformer can actually, the loss can actually go down a lot lower, both in train and test, than these models?
It seems like in test, they all converge around the similar test loss. I'm not sure about training loss.
Yeah.
But it seems to be, here they say it's like comparable training test losses, like around 1.55.
Maybe I was reading the graph differently, but yeah. Yeah, it's, I would have wanted to see like a table that shows, you know, we have chosen this hyperparameter for training.
Yeah.
We tried others and these were the results.
I wonder if maybe I missed it in the appendix.
Nowadays papers are longer in the appendix than the main content.
Yeah, so they have some. Okay, they have some examples about the parameters, but yeah, I'm not sure. Transformers configured with 6 heads. I don't know. I guess they use the same parameters, the same learning rate and everything for all of them.
Makes sense.
Seems, yeah. But yeah, I would have loved to see some kind of ablation study of those. Yeah, so I guess this kind of covers like what we've seen before, or what I've mentioned before, which is the previous models. And what they're trying to get at here, so I described here that, you know, S6, which is the new Mamba, was this like, where they made the transition matrices input dependent, which increased like the ability to learn more complex tasks. They also look at recurrent versions of attention. As I mentioned, I haven't really looked into this very much, but they make an interesting observation here, which is that basically, like when you look at all of these models, the recurrence patterns actually like quite similar. So if you look at like a Mamba model, you basically have this like these matrices A and B, which take in a previous hidden state, and the input, which looks quite similar to what you have with a GRU and an LSTM. The difference is basically how, like, what are these transition, or what are these, like, how are the transitions learned basically from one hidden state to the next based on the input, which I thought was quite interesting. So they all have like, they're all sort of recurrent in nature, and the difference is how you learn these transitions. Yeah, they also give they actually give the PyTorch implementations at the bottom in the appendix, which are actually like quite simple, because I guess like they've even simplified what an LSTM and a GRU is. So building these yourself would be simpler than before. And yeah, and so that's the paper. I guess, like, as I mentioned, it's an interesting idea. It's an interesting exploration. I think for me, the bit that stands out is the fact that we can actually simplify these like recurrent neural networks to make them more efficiently trainable, but actually they seem to perform well on these different tasks. I would have also liked to see, I would have liked to see a lot of things, but I think I would have also liked to see, for example, whether like a performance of LSTMs and GRUs on these tasks, although I don't know if basically they're just intractable, like you can't actually train them on these kind of tasks because they're too long, the sequence lengths are too long. So maybe it just wasn't feasible to actually train an LSTM or a GRU on these tasks. I guess that would make sense. But yeah, I would have loved to see some more studies and examples.
I was going to say that they motivate the idea that they haven't looked at more transformer models because of like the computation limitations. So they didn't have access to larger GPUs. I think it was like this one. Yeah, maybe it's like a smaller lab that doesn't really have that much compute behind them.
That's fair. Yeah, that's fair. So I do wonder where it'll go, and whether this will get more people looking at these kind of enhanced RNNs.
Can I ask a question?
Of course, yeah.
It's probably very difficult to answer, but what interests me most is always the possibility of getting to a new kind of frontier model. Can you have a stab at whether you think this will ever get to be some kind of a challenger to a frontier model?
Yeah, it's a good question. I mean, I suppose like what is required to be a frontier model? Like in my head, we've seen like Mamba and Mamba style architectures come out, and they were supposed to be a challenger to transformers, but maybe, I guess like what's left to see is like there's these papers where they seem to perform on par with transformers on these smaller tasks, but I guess I wonder how well they scale to billions of tokens or trillions of tokens and billions of parameters, and maybe, I don't know, maybe that's where they falter, but I have no idea. And maybe our hardware is built better for transformers than it is for these models. I'm not sure. I have no idea about that, by the way.
Because I was very excited when Mamba and other things like that came out, but I haven't seen anything in the last few months. I may have missed it, but I do stay pretty closely watching this because I keep hoping for a Mamba frontier model. And by frontier model, I think it's something like it needs to be able to be almost or as good as a Sonnet 3.5, GPT-4o, or even better 1.0 preview. You see what I mean? It needs to be somewhere near there, or Llama 3.1405, that kind of thing. That it's that kind of level. I mean, it's easy if you're using much simpler and smaller models, 1, 2, 3, 4, 5 billion parameter models. Those are working pretty well now, but they fall down on the really difficult tasks. And anyway, I'm always doing really difficult tasks, so I don't actually use the smaller models all that much. I'm constantly waiting for the next upgrade from OpenAI or Anthropic, because these are the really hard tasks. So that's what I'm interested in, and obviously it's early days for this, but I will be interested to see. And I'm always excited when something like this comes out, but then usually later I'm disappointed because there isn't enough. Maybe it's just the usual thing of the frontier models now are so big and powerful. It's very hard. It would actually require a lot of money, therefore and that means a lot of compute for something like this to be scaled up. So maybe the barriers to entry are pretty high, and unless Facebook or Meta decided to take it on, or maybe Nvidia, then maybe it's just going to die in the dust. Anyway, thanks very much for going through this.
Damien, did you have a point?
Yeah, I think I was about to say, with the barrier to entry, I think that's the main blocker for these sort of architectures, is that someone needs the compute backing to be able to be like, oh, this is interesting. I want to dedicate, hundreds of thousands of dollars to now run it on this cluster, which makes me think that maybe distributed compute and there's now like some of these blockchain backed networks that allow you to hire computation essentially across the world. It might be slower, but might be possible for someone who wants to leverage a lot of compute but doesn't necessarily have the access. So I think it's converging in that direction, where people will be able to do these sorts of large experiments and show that these networks are potentially challenges to like GPT-4o or 1, as you said. But I think it'll take time for the hardware and the infrastructure to catch up to what we want to do with these models, because at the moment it's very gated to massive companies with huge resources.
Yeah. There's also this paper. I was looking through a few Twitter threads that were talking about this paper, and it kind of sparked a debate, actually through a tweet that Francois Chollet wrote, who's the creator of Keras, which is saying that so he believes, he's on the camp that actually we're bottlenecked by data set, not architecture. And he proposes that the fact that we've seen these different architectures achieve comparable performance, he sort of believes that actually the limitation to better models is actually our data set, not novel architectures. Whereas other people are like, actually, we're still bottlenecked by parts of the architecture, and that's what we should research. So there's kind of an interesting debate online about what's holding back like new, better performance. Is it looking at different architectures, or is it looking at better ways to learn from, or better ways to curate maybe the data set that improves the performance of these models?
It almost seems like we need new technology that can scour the internet or start asking questions on the internet and then collecting answers to give us more data, because at the moment the half of the internet is already polluted by AI stuff. So
yeah, I know.
we need quality data.
More quality data,
yeah. What we really need to do is to be able to scan millions of books and use those. They GPT, OpenAI obviously use books, and I guess Anthropic does as well, but not nearly enough. And books are generally a much better curated set of data. I mean, factual books. I mean, okay, fine, fiction, but I mean, we're talking about facts here. So that's the missing thing. And also, there are millions of papers out there, and those, and especially if they've been peer reviewed, those have also been fact checked quite carefully. And I don't see those being used enough. And maybe I'm wrong, but if I am right, then I'm not sure why.
Cool. Well, maybe that's a good place to leave it for today. But thanks so much for joining Paper Club. We'll see you next time.
Thank you, Gerard.
Thank you, Gerard. That was really cool.